Okay, so today we're going to start to talk about different types of forces, and there are really three forces that we see in act on us every day. Today we're just going to do the first one, which you already know a fair bit about. It's known as the gravitational force of attraction, in other words, the force of gravity. And all forces, our symbol for them throughout high school physics is a capital F with the subscript that tells us what it's from. So the force of gravity, or the gravitational force of attraction, is a capital F with a subscript G. Now there's another name for this force, but I'm not going to say it yet. We're going to talk about it first, and then we'll come back to that other name. If you're lucky, I'll remember. You're not in the room with me to remind me, so I'll put a blank there to try to remember. Now, you all know the force of gravity. You know it acts on things. You know that it's why when you let something go, it falls. If you were to ask someone, what's the force of gravity? And if we were in class, I would say that exact question to you. And the majority of people, especially the unphysicsed among us, would say that it's the force that the earth puts on an object. And they wouldn't be wrong. They just wouldn't be totally right. So without a question, the force of gravity is a force that Earth puts on an object. It's what's holding us down. Earth's gravitational force of attraction on you and I right now are why we're not floating up in the air. But that definition is too narrow, because I could say to you, well, what causes the tides? And I would think a lot of you would say the gravitational force of attraction of the moon. And what is keeping the earth revolving around the sun? Well, that's the gravitational pull of the sun on the earth. So to say that the force of gravity is a force of attraction of the earth isn't wide enough. And really, in the end, it was Sir Isaac Newton that figured out gravity. Okay? And what Newton said, and the law, and what we're going to get to, is the universal law of gravitation, and it's Newton's universal law of gravitation. So what Isaac Newton said, he expanded it. He said the gravitational force of attraction is the force of attraction the force of attraction between any and every two objects in the universe. Between any and every two objects in the universe. So even as I'm writing this, I am putting a gravitational force of attraction on you. On each one of you, plus on the people who are working at the takeout in McDonald's, and on the people who are walking on the walking trail, okay? And you are too. This force of attraction is between any and every two objects in the universe, okay? Now, when Newton was suggesting this, and you know that Newton worked on gravity because I'm sure you've heard the apple falling from the tree. The story says it hit him on the head, but I'm not so sure that part's true, but I think it was him watching the apple fall that helped him. And it helped him because, and I just need to do a little aside, because back then people were good with what were called contact forces. People understood force when they saw someone smuck someone hit someone push something. Those were contact forces, and they understood them. But when Newton tried to say there was another whole category of forces called non-contact forces, and these were the ones that were causing the apple to fall from the tree, people were like, excuse me, how do you think the earth is causing that apple to fall from the tree when the earth isn't even touching the tree? And so it took Newton a bit to convince people that there was a such thing as non-contact forces. So we know the force of gravity is one of them. We also know they exist in other spots. If you've ever held a magnet and a paper clip and brought the paper clip closer to the magnet, you know that it doesn't have to touch the magnet before it feels that force, and that if your magnet's strong enough, it'll pull the paper clip out of your hand and bring it to the magnet. We also know there's a force of attraction, or a non-contact force, attraction or repulsion, between charges. You would have done that in 9th grade electrostatics when you had like two charged particles. You know they don't have to touch in order to attract each other or repel each other. So 300, going on 400 years later, we know Newton was right, that there's such thing as non-contact forces. But back then in 1650s, it was a little rougher sledding for him. Okay, so back to what he said. So he said the gravitational force of attraction is a force of attraction between any and every two objects in the universe. And what he figured out was that it was dependent upon the mass of the two objects and on the distance between them. And he also figured out there was a constant there. This is Newton's universal law of gravitation, okay, this equation. Now I'm showing it to you so that you understand our simplified version that we're going to be using all throughout grade 11 and until we get to planets and stuff in grade 12. Okay, so this is where M1 and M2 are the masses of the objects. R is the distance from the center of one object to the center of the other. Distance from center of one object to center of the other. And of course, mass is measured in kilograms, and distance is measured in meters. Now this distance from the center of one object to center of the other might seem like, okay, like why, who cares? Like why are we doing this center to center thing? Well, we're doing this center to center thing. If I picked the two of you and measured the distance between you, whether I put the meter stick on the outside edge of your tummy or shoved it all the way into the center a bit, it wouldn't make a really big difference on our R. But if we're doing the gravitational force of attraction between you and the Earth, it's going to matter if I measure to the outer edge of the Earth or if I measure to the center of the Earth. Okay, so that's why we say center to center. And it's a distance, but it's denoted as an R, because imagine if we were in class and I was doing this force between two of you sitting there, one of you could get up and you could walk around the other person. So this is the distance center to center. But if one of you walks around the other person, staying the same distance, then obviously the R is a radius. Okay, so this force will be the same no matter where you are on the circumference of that circle. Okay, so that's why it's center to center. And G is a universal constant. It is the same no matter where you are in the universe. It is equal to 6.673 times 10 to the negative 11 Newton meters squared per kilogram squared, no matter where you are in the universe. Okay, and then when we put these together, we'll get Fg. So let's do it. Let's do it for a couple of you. So let's say our M1, let's say one of you is 60 kilograms, and let's say the other one of you is, I don't know, maybe 80 kilograms. And let's say you are about, this is before social distancing time. Oh, maybe we better make it socially distanced. So we'll say you're 2 meters apart. And so then the question is, what is the gravitational force of attraction between you? So Fg is equal to G M1 M2 over R squared. So Fg is equal to 6.673 to the negative 11 Newton meters squared per kilogram squared. And don't worry, you won't have to memorize this constant. I just want to show you so you understand